interaction I'm going to talk about, and the one that is most important in terms of X-ray production in radiology, is Bremsstrahlung interaction. And this is where an electron with enough energy can penetrate all the way to the centre of the atom and interact with the nucleus. I'll illustrate this once again with tungsten. So let's say, for example, you have an electron with 80 kilo electron volts worth of energy that's able to penetrate through the outer electron clouds to reach the area around the nucleus. As it nears the centre, the electrostatic force of attraction from the nucleus slows it down, and the kinetic energy that is lost is emitted mainly in the form of heat, but also in the form of electromagnetic radiation. Bremsstrahlung actually means braking radiation, so the process gets its name because it's the radiation that's released as the electron slows down. The amount of energy released from each interaction can be a continuous range from 0 to the full energy of the incoming electron, which would happen if it was suddenly stopped dead and released all of its kinetic energy at once. So in this example, the maximum energy of the X-rays would be 80 kilo electron volts. This is in contrast to the discrete energy levels of characteristic radiation. The likelihood of Bremsstrahlung increases with atomic number, as the higher the atomic number, the stronger the pull on the transiting electrons. It also increases with the kinetic energy of the electrons, as higher energy electrons are more likely to reach the nucleus. They also produce higher energy X-rays as well. So that's the theory of X-ray production basically covered. Now this is just a schematic diagram of an X-ray machine, and I've labelled some of the important components to it. The cathode is where you get your electrons from. It's made of thoriated tungsten, and its desirable properties include a high melting point, the fact it emits electrons readily, and the fact it doesn't vaporise easily, which is important given the high temperatures it's heated to. At the opposite end you have the anode, which is made of tungsten. As previously discussed, it's chosen because of its high atomic number, which means it's more likely to cause Bremsstrahlung interactions. A peak voltage of 90 kilovolts, known as the kVp, is applied between the cathode and anode to accelerate the electrons across the vacuum to 90 keV. Around the cathode is a focusing cup. The electrons emitted from the cathode have a tendency to repel each other and spread apart, which is a process known as blooming. This increases the area of the tungsten target they strike, which results in more geometric unsharpness. The cathode is therefore surrounded by a cup which is also negatively charged to in essence repel the electrons back together and stop them spreading apart. If the negative charge of the focusing cup is great enough, it can actually prevent the emission of electrons altogether, and this can be used for rapid control of X-ray emission, known as grid control. The components are held in a glass envelope, and this is surrounded by oil to conduct the heat away. Outside of this is a lead-lined metal housing. X-rays are emitted from the target in all directions, so the lead has to keep leakage of X-rays from the tube to below 1 milligray per hour at 1 meter. There's a small window in the housing to allow the useful X-rays out.